welcome to the third of our tutorials on different differentiation rules. This lesson will be on the quotient rule. Previous to this we've looked at the product rule, and before that we kicked off with the chain rule. So our quotient rule is going to be used to differentiate quotient functions. Now again, quotient functions we've met before, but now we've got a formal definition for them. We're going to look at a polynomial here of 3x, so a really simple function, and x cubed plus 7x on the bottom. So this will be an example that we'll engage throughout the lesson. And we're going to introduce the quotient rule. Now it's a complex, rather messy looking formula, and it's important we get this correct. However, looking at the steps here, similar to the product rule, we need to define u as being the top part of our function and v as being the bottom part of our function. Now with the product rule, it didn't matter which order we had. If we multiply two numbers, 2 times 3, doesn't matter the order. 2 times 3 is the same as 3 times 2. However, with quotient functions and division, we need to get the order correct. 1 divided by 2 is a half, 2 divided by 1 is 2. They're different answers. So we need to make sure we correctly define u as being the numerator and v as being the denominator. If that's the case, our quotient rule we state it as dy dx equals v times du dx minus, so we've got a sign change here, minus u times dv dx all over v squared. So quite a complex function. Again, it'll be on your formula sheet in the methods exam at the end of the year. Again, I've left this from the previous set of notes. Again, through this process we may need the chain rule as well. So you can see a complex looking formula like that and possibly a chain rule thrown in on top can be quite a difficult problem in terms of the set out. The mathematics and the concepts are not difficult, but the set out, it's important we get that correct. So the example we're going to use here is the 3x over x cubed plus 7x. And we need to define u as being our numerator, 3x, and v as being our denominator, x cubed plus 7x. Second process, step 2, is to differentiate each of those. So nothing different to the product rule. Define u and v and differentiate u. We get 3. Differentiate this cubic, we get the quadratic 3x squared plus 7. They're going to be the 4 parts. If we look at our formula again, we've got v, we've got u, and we've got the differentiation of each part, and we've got v squared on the bottom. And now we need to write our formula again. Now I've taken a little bit of a shortcut here. We don't want to, if we can help it, write that whole formula out. It's only part of our process. We just need to make sure we get the order of operations correct. So I've abbreviated to u dx to u dash, similar to the function notation you're familiar with fx and f dash x, and the v dx. Again, all these differentiations are with respect to x, so v dash is the same as dv dx. So a little bit of shorthand notation there just to get the order correct for our substitution. On the denominator we've got v squared as well. Substitute into the formula. So again, we've got everything ready to go, the 4 parts ready to go, and we're also going to use v squared on the bottom of our function. Keep it in brackets because with our expansions we're going to have to be careful, and we're also going to have to be careful with that negative sign there, particularly if there's any negatives within that differentiation form there. So dy dx equals that put together, and then step 5, we've got it ready to go, we just need to simplify it here. So simplifying the top, expanding these brackets, we've got 3 lots of, and 3x lots of to give us that on the top line. Again, as I said before, be careful with the directed numbers, with the negative signs. And on the bottom, we're just going to leave this as v squared. So x cubed plus 7x all squared. There's no need to further engage with this at this stage. Simplifying the top row worked out quite nicely. We had plus 21x and minus 21x. Won't always be the case, but they cancel out, leaving us minus 6x cubed on the top. Now that's pretty much ready to go. The only thing I notice here is we've got lots of x's on the top and lots of x's on the bottom. So there is a common factor within this bracket here, and we can take out x out of both these terms. So I've taken x out, leaving me with x squared plus 7, all squared. So if I want to take this x out the front here, I would need to square it first. So x squared would slip out the front of the bracket, meaning I have an x squared on the top, x squared on the bottom, and an x cubed on the top. 6x cubed divided by an x squared would leave me 6x, or negative 6x on the top of that fraction. So if you're checking that work on the CAS calculator, your CAS will obviously do that factorisation and cancelling down for you. But it's important to note if you're doing these exercises and you're checking the back of the book, you may get slightly different varieties of answers. It's a good process to actually see if you can't get your answer to the final answer in the back of the book. It doesn't mean to say this answer or that answer is incorrect. Even that answer is algebraically and numerically correct. But it's a good practice to actually get down to the simplest form we can, without over-engaging and making a risk of making further mistakes in the question. So that is the quotient rule. Stems from this particular rule, v times du dx minus u times dv dx all over v squared, and And the application, very similar to what we've done previously with the product rule and the chain rule, is to be nice and neat in our set out, clearly define what we want, substitute in, simplify, job done. Okay, thank you.